Hello students, welcome to DEY'S learning. Today we are starting solution chapter. Our today's lesson we are covering the following topics. Number one is vapor pressure of liquid solutions, Raoult's law of solutions for non-volatile solute in volatile solvents. Number three is Raoult's law of solutions for solutions in which there are two volatile solvents. Okay, let's go one by one. Our first topic is vapor pressure. Number one is vapor pressure. Now, obviously, the first question is what is vapor pressure? I can draw a diagram in a very simple manner. Let us consider a system in which a liquid is present in a container, and this container is present inside a thermostat, so that no heat can be transferred from outside into the container or vice versa, or no heat can be transferred from the container to the surroundings. And this is your vapor, the vapor of the liquid. So this is liquid and this is vapor. Okay. Now, if the liquid is kept inside the container, what will happen? Some liquid will be evaporated. So evaporation will occur, and if we kept this vapor inside the container, what will happen? After a period of time, this vapor will be condensed to form the liquid again. So the formation of a vapor from the liquid is known as evaporation. এই ঘটনাটাকে বাষ্পায়ন বলে, and when the vapor is condensed to the liquid phase, this process is known as condensation. এই ঘটনাটাকে ঘনীভবন বলে. And a time will come when this rate of evaporation and the rate of condensation will be equal. একটা সময় আসবে যখন এই বাষ্পায়ন এবং ঘনীভবন দুটো সমান হারে চলতে থাকবে. And that time the pressure created by the vapor on the liquid is known as vapor pressure of the particular liquid. সেই অবস্থায় যখন সাম্যাবস্থা আসবে, সেই অবস্থায় এই বাষ্পটা তরলের উপর যে চাপ প্রয়োগ করবে, সেই চাপটাকে বলা হয় ওই তরলের বাষ্পচাপ. সো বাষ্পের চাপ সুতরাং বাষ্পচাপ, এটা বাষ্পচাপ নয়. The vapor pressure is called at that time when the rate of evaporation and the rate of condensation will be equal. So we can write the rate of evaporation, will be equal to the rate of condensation. At that time, this is the condition of an equilibrium. এই equilibrium টা exist করবে. This is the condition of an equilibrium. And at the equilibrium state, the pressure exerted by the vapor on the liquid is known as vapor pressure. How can we measure that? If we connect this container with a the complete system is known as actually manometer. In the manometer tube there is a mercury column, and of course there will be atmospheric pressure, and this height, due to the presence of the due to the pressure of the vapor, this mercury column will come down, and the difference between the height of the two mercury column is actually h, and from P equal to h rho g we can measure the vapor pressure of this liquid. So we can write the definition of vapor pressure. We can write the pressure exerted by the liquid at the equilibrium the pressure exerted by the vapor at equilibrium on the liquid at a particular temperature. Is known as vapor pressure. Is known as vapor pressure of the particular liquid. Okay, we considered the factors on which the vapor pressure of the liquid depends. So the factors on which vapor pressure depends. যে শর্তের উপর বাষ্পচাপ নির্ভর করে, it depends on actually two factors. Number one is the nature of the liquid. This is very important. The nature of the liquid. Of course, vapor pressure depends on the nature of the liquid. More volatile will be the liquid, greater will be its vapor pressure. এই লিকুইডের এই তরলটা যত বেশি উদ্বায়ী হবে তত তার বাষ্পচাপ বাড়বে, যত বেশি উদ্বায়ী হবে তত বাষ্পের পরিমাণ বাড়বে এবং বাষ্পচাপ বাড়বে। So it depends on the nature of the liquid. Of course, the vapor pressure of ether is greater than that of water, because in water there is hydrogen bonding. জল যদি হয় তাহলে হাইড্রোজেন বন্ডিং থাকবে, ইথার যদি হয় তাহলে হাইড্রোজেন বন্ডিং থাকবে না। So the vapor pressure of ether will be greater than that of water. So it depends on the nature of the liquid. And second point, it depends on the temperature. Definitely vapor pressure depends on temperature. Greater will be the temperature, more number of molecules of the liquid will go into the vapor phase, and so that the vapor will create more pressure on the liquid, so the vapor pressure will be increased. যত উষ্ণতা বাড়বে বেশি পরিমাণ তরলের অণু গ্যাসীয় অবস্থায় বাষ্প অবস্থায় যাবে এবং বাষ্প অবস্থায় গিয়ে বেশি প্রেশার ক্রিয়েট করবে, ফলে বাষ্পচাপ বাড়বে। So it depends on the two factors, nature of the liquid and temperature. Next, the quantitatively there is a relation between the temperature and vapor pressure of the liquid. এই উষ্ণতার সঙ্গে বাষ্পচাপের একটা সম্পর্ক আছে। and this quantitative relation is given by Clausius and Clapeyron. So we can write quantitatively vapor pressure is related to temperature. Temperature by the renowned equation Clausius-Clapeyron equation. Clausius-Clapeyron equation. The derivation of the equation is out of syllabus. The relation is d ln p dt equal to del H by R into T square. Sometimes this is del H of vaporization, of course. That is the enthalpy change of vaporization. This relation is known as Clausius-Clapeyron equation. The relation is known as Clausius-Clapeyron equation. So the vapor pressure P is related to temperature. This is latent heat of vaporization, or means universal gas constant. And if we integrate this equation, within certain limit, we can manipulate this equation as d ln p equal to del H vaporization by RT square into dt. Okay, so on integrating this equation, on integration, within proper limit from P1 to P2, d ln P equal to del H vaporization by R, assuming that this del H is independent on temperature, definitely from T1 to T2 dt by T square. Okay. So on integration, we can write in a single step ln P2 by P1. This is equal to del H vaporization by R minus 1 by T. This is 1 by T1 minus 1 by T2, right? This one is not incorrect, definitely not. So then we can write log to the base 10 P2 by P1 equal to del H vaporization 2.303 here, 2.303 R into 1 by T1 minus 1 by T2. So this is the integrated form of Clausius-Clapeyron equation. This one is very important for JEE Mains, NEET and other competitive exams. Now going forward to our second point, number 2. Raoult's law. For solution of non-volatile solute in volatile solvent. In a volatile solvent. Okay. Raoult is a French chemist who has given the law. Let us consider two solutions. Here is a pure solvent like water, ether, acetone, whatever may be. Here is your pure liquid. Of course, the liquid is volatile in nature, which can evaporate. যে তরলটি বাষ্পায়িত হতে পারে, মানে উদ্বায়ী তরল আর কি। And here the pure liquid contains, it is a solution where the pure liquid is present. This pure liquid, the same liquid is present here and here, and here some non-volatile solute. Say some non-volatile solute is added into the pure liquid, so that a solution is made where the non-volatile solute is present in the volatile solvent. Okay, so actually the nature of the solute we can write here. The nature of the solute, this non-volatile solute, the nature of the solute will be, number 1, non-volatile. Non-volatile, non-electrolyte, and number 3 is solid. ওই দ্রাবটিকে হতে হবে অনুদ্বায়ী, অতড়িৎ বিশ্লেষ্য এবং কঠিন। নন ভোলাটাইল, নন ইলেক্ট্রোলাইট solid solute is present in this volatile solvent. So what will happen? How the vapor pressure of the liquid will be affected? Now if pure liquid is present here, only the pure liquid molecules will be present over the liquid. So it is the vapor of pure liquid, and of course here also the vapor must contain only the pure liquid, that is the solvent, because the solid is non volatile. দ্রাবটার তো অনুদ্বায়ী, সুতরাং দ্রাবটা কখনো ভেপার ফেজে যাবে না, ভেপার ফেজে যাবে শুধুমাত্র লিকুইডটা। সো এই লিকুইডটা এখানে যে ভেপার তৈরি হয়েছে, এখানে যে ভেপার তৈরি হয়েছে এবং এখানেও যে ভেপার তৈরি হয়েছে, the two vapor of course contain the same liquid, only the pure liquid molecules are present there, because the solid molecules will not go into the vapor phase because it is non-volatile in nature. Now what will happen? এখানেও এই তরলের বাষ্প আছে, এখানেও এই তরলের বাষ্প আছে। My question is, will the vapor pressure will be same in both the cases? What do you think? Of course the vapor pressure will not be same. If the vapor pressure here is P0, sometimes it is written as P01, I can write here. The vapor pressure of the pure liquid is designated as P01, and the vapor pressure of the solution is designated as P1. It is a pure solvent, vapor pressure of pure solvent, so it is P01, 0 designated the pure solvent, and here the vapor pressure of the solution is designated P1. Of course this P1 will be less than P01. Question is why? There are two main reasons why the P1 is less than P01. Of course this P1 will be less than P01. Now the question is why? The quantitative relation is given by Raoult, but first of all we consider some qualitative reason why the P1 is less than that of P01. P1 টা P01 এর থেকে কম। প্রশ্ন হচ্ছে কেন? আমরা আগে একটু কোয়ালিটেটিভ ওয়েতে একটু ভেবে নিই। The reason is, that is আমরা যদি ল্যাঙ্গুয়েজে বলি, the vapor pressure of the solution is less than the vapor pressure of pure liquid. The question is why? I can write the reason over here. The reason is that number one, we know there are two types of forces. One is adhesive force, the other is cohesive force. একটা বলে সংশক্তি বল, আর একটা হচ্ছে আসঞ্জন। We know always the adhesive force is greater than cohesive force. আসঞ্জন বল সংশক্তি বলের থেকে বেশি। Here which one is the adhesive force and which one is the cohesive force? Now look at here very carefully. In the pure liquid, say this is water molecules, only water molecules are there. So the attraction force among the water molecules is known as the cohesive force, সংশক্তি বল. But here the adhesive force acts because these particles, these solute particles are attracted by the surrounding solvent molecules. এই দ্রাবের অণুগুলো পার্শ্ববর্তী দ্রাবকের অণুগুলো দ্বারা আকর্ষিত হয়. The attraction force among the same particles are known as cohesive force, and the attraction force among different particles is known as adhesive force. So here the adhesive force, that is the attraction force among the solute and solvent molecules, this is the adhesive force here, is greater than the attraction force among the solvent molecules only. শুধুমাত্র দ্রাবকের অণুগুলির মধ্যে যে আকর্ষণ বল তার থেকে দ্রাব এবং দ্রাবকের অণুগুলির মধ্যে আকর্ষণ বল বেশি. সো actually the solute particles attract the molecules of the solvent behind so that it can't go into the vapor phase. মানে দ্রাবের অণুগুলি দ্রাবকের অণুগুলিকে নিচের দিকে আকর্ষণ করে যাতে করে দ্রাবকের অণুগুলি বাষ্প অবস্থায় যেতে না পারে. So the vapor pressure actually decreases because less number of molecules will go into the vapor phase. So this is reason number 1. And the second reason is, I can write here. And the second reason is, look at here, when pure liquid was present, only the liquid molecules were present at the surface. But when the solutes are added to the solvent, some solute molecules are present on the outer surface. We know vaporization occurs from the outer surface, evaporation occurs from the outer surface. বাষ্পায়ন একদম উপরিতল থেকে হয়, সেই জন্যে এখানে উপরিতলে শুধুমাত্র দ্রাবকের কণাগুলি ছিল, কিন্তু এখানে উপরিতলে দ্রাবক এবং দ্রাব উভয়ের কণাগুলি আছে, যার ফলে on the outer surface the fraction of molecules of the solvent is less. ফলে এখানে দ্রাবকের অণুগুলির যে মোল ভগ্নাংশ উপরিতলে আছে সেটার পরিমাণ কম. So say here the 100 molecules will be present in the outer surface, and here 80 molecules will be present in the outer surface. So we can write the outer surface of the solution contains less number of solvent particles. Less number of solvent particles than that present in the pure solvent. So these are the two reasons why the vapor pressure of the solution is less than the vapor pressure of pure liquid. So let's proceed to the Raoult's law. What Raoult has said quantitatively. Raoult said that this P1 is equal to x1 into P01. It is a Raoult's law. Simple, very simple. P1 equal to x1 into P01. What is x1? x1 is the mole fraction of solvent in the solution. Okay, x1 is the mole fraction of the solvent in the solution. So, of course, x1 equal to P1 by P01. Very simple. This one is a relation known as Raoult's law. We know the value of x1 will be of course less than 1 because the summation of x1 and x2 will be equal to 1. This is the mole fraction of the solvent and this one is the mole fraction of the solute. Summation of these two is equal to 1. So x2 will not equal to 0 because it is a solution of two components. So x1 must be less than 1. So if x1 be less than 1, then we can write, of course, P1 is less than P01. We have learned from our previous learning, P1 is less than P01. So this is Raoult's law for solutions of non-volatile solute in volatile solvent. So going forward to our third point, this is Raoult's law of solutions of two volatile components. Now let us consider a solution like this. Where two components are present and both are volatile in nature. So we can write, in the vapor phase, both the molecules, say the black is represented by solvent number 1 component, the black ink represents first solvent and the red ink represents second solvent. So in the vapor, both the molecules of the components will be present. The vapor contains both the molecules of the two components because both the liquids are volatile in nature. So what will happen there? So the vapor pressure will be the vapor pressure of the complete solution is written as P total or sometimes only capital P. This P will be equal to the pressure of vapor pressure of first component plus the vapor pressure of second components according to Dalton's law. because here the pressure of the first component is P1 and the pressure of the second component, say it is P2, small P2. So the vapor pressure of the complete solution will be P1 plus P2 according to Dalton's law. Okay, now from Raoult's first law we can write this P1 equal to x1 into P01, because P01 is the vapor pressure of the pure solvent. Only when solvent 1 was present, then the vapor pressure of the solvent will be P01. And here the x1 is the mole fraction of the solvent number 1. And x2, P2 equal to x2 into P02. This x2 is the the mole fraction of the second solvent in the solution. So x1 and x2, so this one will be capital P. So x1 and x2 are the mole fractions of the components in the solution. Sometimes this equation can be written as P equal to XA P0A plus XB into P0B. The same thing, of course, the first solvent is taken as A and the second solvent is taken as B, nothing else. Okay, now we can manipulate this equation as P equal to one minus XB into P0A plus XB into P0B. We know, of course, XA plus XB is equal to 1. Of course, the mole fraction of the two components, the summation of mole fraction of the two components will be, of course, 1. Next, P equal to, this one is capital P and these two are small p. So we can write P0A plus XB into P0B minus P0A. So these two are very important relation to draw a graph. This one and of course this one. Now we can draw a graph. Let's draw the graph of Raoult's law of solutions of two volatile components. Okay, the two equations we have for a solution of two volatile components, we have total pressure P equal to XA P0A plus XB P0B, and the modified form of the equation is P equal to P0A plus xb into P0B minus P0A. So these are two equations from which a graph can be made. Okay. In the graph, this axis is actually PA axis. That is the pressure of component A. And this axis represents, this side of the axis represents the pressure of component B, PB. I can write PB here. Okay. And this axis represents the mole fraction of components. I can write here XA is equal to 1, so that XB is equal to 0. And at this point, XA is equal to 0 and XB is equal to 1. Okay. So mole fraction is increased and decreased on both sides with respect to different components. Okay. So look at the line from here. At this point XA equal to 0. As the value of XA increases, the value of PA increases, and at this point the value of PA is P0A. The value of PA is P0A at this point. That is the vapor pressure of A component in pure solvent when only A was present. And this line, so this line actually presents PA equal to XA into P0A, this line. And at this point XB equal to 0, and at this point XB equal to 1. So the value of mole fraction of B component increases from here to here through this line. So we can write this equation here. PA equal to XA into P0A, and this line represents PB equal to XB into P0B. Okay. So the value of, at this point XB equal to 1, so that PB equal to P0B. So at this point the value of PB is P0B. That is the maximum value of PB. Okay. So this line represents PA equal to XA into P0A, and this line represents PB equal to XB into P0B. So what about this line? Can you tell me? This line represents capital P total. Capital P equal to XA into P0A plus XB into P0B. Okay. The modified form of this equation is this one. We can explain this graph from this equation. Look at here. This is the equation of the form y equal to, this one is C plus mx. Simply this one is the equation of the form y equal to mx plus c. So here x equal to xb and y equal to equivalent to p. So this one is c. So look at here, xb, the value of xb is increases from 0 to 1. So as the value of xb increases, so when the value of xb equal to 0, this portion equal to 0, so p equal to p0a, this is the value of P when xb equal to 0. When xb equal to 0, P equal to P0a. And as the value of xb increases from here to here, as the value of xb increases, the slope is positive slope, that is P0b minus P0a. We have arbitrarily taken here P0b is greater than P0a. It is taken arbitrarily. It is taken arbitrarily. Okay. P0b is greater than P0a. Here P0b is greater than P0a. So P0b minus P0a, this one is a positive slope, and x. So m, the slope is positive here. So this equation correctly represents this equation, P equal to xa into P0a plus xb into P0b, and this line represents the equation. Okay, we can understand this graph with some another aspect. Take a perpendicular, draw a perpendicular over there. Say for example, at this point, the value of xa, say 0.2, and the value of xb is say 0.8 at this point. So at this point the value of xb is fixed, so this represents a particular solution of a particular composition where xa equal to 0.2 and xb equal to 0.8. So for that solution of that particular composition, we can designate some name here. Say it is P, at this point it is P, at this point it is Q, this is R, and this point is S. So for the solution of that particular composition, we can write for that particular composition, we can write PQ is equal to PA and PR equal to PB, and of course the complete line P is equal to PQ PQ plus PR. We can write from the point of view of geometry, from the congruency of the triangles, that PQ is equal to RS, of course. PQ must equal to RS plus PR. So PS represents the total pressure of the solution P. RS represents the RS or PQ represents the pressure PA, and PR portion represents the pressure PB. So we can derive Dalton's law from the graph also. So this is a trick over here. This PQ portion, this portion will be equal to RS. You can try it from the properties of triangles, from the geometrical point of view. Okay. Now there is a case of vapor phase composition. Point is vapor phase composition. Very important topic. Vapor phase composition. Many questions are asked from this portion in competitive exams. First, take the concept from here. Say there is a mixture of two solutions. This one is solution A, the black one represents solution A, and the red one represents solution B. Represents solution B. And of course both are volatile in nature. So in the vapor phase, the particles of both A and B will be present. Of course that both are volatile in nature. দুটো দ্রাবকই উদ্বায়ী, সেজন্য বাষ্পীয় অবস্থাতেও দুটো পদার্থই উপস্থিত থাকবে, এর মধ্যে এও থাকবে বিও থাকবে. We can write here XA and XB, these two are mole fractions in the solution phase. In the solution phase or liquid phase. In the solution phase or liquid phase. Now the question is, of course this is a vapor and the vapor contains both A and B. So there will be a mole fraction. These two mole fractions are YA and YB. Of course these two are mole fractions, and this is the mole fractions of the vapor phase. The vapor phase contains both A and B, and the solution phase contains both A and B. XA and XB are the mole fraction of A and B in the solution phase, in the liquid phase, and YA and YB are the vapor, are the mole fractions, in the vapor phase. So we have to make a relation between the the questions are asked so that we have to calculate the mole fractions in the vapor phase. Now from Dalton's law we can write the mole fraction of YA in the vapor phase will be the pressure of component A divided by total pressure P. Because here both A and B are present, the A component exert pressure PA and B component exert pressure PB. So YA equal to PA into total vapor pressure of the solution. This is capital P, and this PA can be written as XA into P0A divided by capital P. And from here, this is a very important relation. You will find many problems from here, and from here we can write XA equal to YA into capital P divided by P0A. Okay. And similarly YB equal to the mole fraction of B component in the vapor phase. This is actually PB divided by total pressure P. This one equal to XB into P0B divided by total pressure P. From here we can write XB equal to YB into total pressure P divided by P0B. So this is our equation number 1 and this is your equation number 2. Now we can make a relation from here. Just omit this one, this part. We know the summation of mole fractions in both the phases. Of course, XA plus XB is equal to 1, and of course we have to write from here, of course, YA plus YB, this is of course equal to 1. This is also the mole fractions. We can write here this one, XA equal to XA plus XB equal to 1. Now from equation 1 we have YA into total pressure P divided by P0A plus XB equal to YB into total pressure P divided by P0B. This is equal to 1, and this implies if we divide the equation, both sides of the equation by capital P, we can write 1 by capital P. This is equal to YA P0A plus YB by P0B. This is a very important relation. This is again a very important relation. Now make a comparison of this equation with our previous equation. Our previous equation was P equal to XA into P0A plus XB into P0B. Now compare these two equations. This one is the relation of the total pressure with the mole fraction of XA and XB. These are the mole fraction in the solution phase, and this is the relation of total pressure P with the mole fractions of YA and YB, which are the mole fractions of the vapor phase. So these two equations are comparable. This one is the relation of mole fraction in the solution phase. This one is the relation of the total pressure with the mole fraction in the vapor phase. This one is actually the reciprocal format. So these two relations are very important. Okay, this is all about for today's lesson. In the next lesson we will learn the positive and negative deviation of Raoult's law. Thanks for watching the video. Thanks a lot.